So indeed, last time I was in this lecture hall, I spent quite a bit of time in this lecture hall in your place, 20 years ago or so. So wow, what emotions coming back to tell you about what I have been doing since. And the title in the booklet, I believe you had, was, do you see it, Statistical Physics of Computation. That was kind of a lazy title, like the first thing that came to my lab. That's the name of my laboratory in EPFL in Lausanne in Switzerland. The more precise title for today will be From Phase Transitions to Machine Learning. And Statistical Physics of Computation is a laboratory in EPFL, so I wanted to show you how beautiful our campus is just next to the Geneva Lake with the view of the Mont Blanc. From my office, when the day is clear like that, you can see the Mont Blanc. And this helps you to kind of situate where actually Lausanne is in Switzerland. And yeah, in computer science, this is the best university there is in Europe. So if you think about what to do after your studies, don't forget about EPFL. Phase transitions and physics. So I will start with a bit of physics. Some things that you have probably seen in your high school. You have probably seen a phase diagram like that. No? What does water do when you change temperature and pressure? So you know that at low temperature and low pressure you have ice, and all possible pressures you have ice, and you have this phase with water and water vapor. What is interesting in that diagram is this is really not pointing far away, never mind, is the critical point up there where actually the transition from water to vapor disappears at high enough pressures and high enough temperatures. So it's kind of interesting. How can a phase transition that is there just disappear? Well, that's what it does. You have the familiar, line with 100 degrees freezing, evaporating at normal atmospheric pressure and 0 degrees freezing at normal atmospheric pressure. But to kind of give in perspective this phase diagram, what the axes actually mean, I love this one. So it's in French, but the only French word that you will not understand there is actually terre. Terre is the earth. So that's the pressure and range of normal temperatures on Earth. And here you have Venus, and here you have Mars. So you can kind of somehow think of this critical point as the conditions close to the conditions on Venus, and these three critical ones close to the conditions you have on Mars. So I thought that's kind of cool. And this is what we see, say, in high school textbooks. Then, of course, in research these days, the phase diagram of water looks more complicated. That's one taken from a recent articles. There are not only 3 phases, but maybe 13, especially at high pressure, the crystalline and solid phases of water. There are many of them, and many of them have mysterious properties, and it's still studied today, and very kind of cool papers are written about it. But that's not what I will be talking about. I will be talking about, more things related to supercooled water. So this was a video in the PDF on this computer. This is not a video. But you can actually do something like that at home. You need to be careful. But put a bottle of water, liquid water, to the freezer. And if you do it carefully, the water will not freeze if it is clean enough. And then you take it out of the freezer. You tap it, like this. You tap it. And then it will suddenly freeze. And you will see the ice growing from one side to the other. And that's the manifestation of the fact that the water was supercooled, and when you tapped it, you introduced some impurity, and around that impurity it nucleated and created the ice. And this manifestation of existence of that, it has other manifestations. So this is not Geneva Lake, that doesn't happen in Lausanne. This is somewhere in China. I heard you can also see this phenomenon of freezing ice in Chicago, next to the Lake Michigan. That's when the rain gets supercooled in the clouds. And then the moment it hits a solid surface, there are always some impurities on the solid surface. It freezes and creates this like crazy looking frozen rain. And one more about these supercooled liquids and metastability, there is this heater that I brought to show you. You use this, either in mountains, if you have a stop and your hands are freezing, you can actually warm with this, or when you have little babies and their belly hurts. So what is this? You see, there is liquid, it's liquid. I actually have a few of them. Maybe you can send them around, there are a few more, so that people can try. And there is a coin inside, a metal coin, kind of a thin one that you can pinch. And what happens when you pinch the coin? So I'll pinch the coin. I pinch the coin, you heard it. And then you see something is growing around. And this is not liquid anymore, this is solid. It's crystallizing and growing. You see the nucleation progressing until all the liquid became solid. And guess what? It warmed. That's why it's a worm heater. And the fact that it warmed, it proves to you that it was metastable, that it is happier energetically as a solid, and hence when it turned solid, it released energy in the form of the heat. And that's the purpose of this little gadget, if you are not a physicist. Of course, if you are a physicist, you are interested, you know, how is that working? So you have several of them, you can try. And where did I put my thing? And question?
Yes, I would like to ask whether that would work even if you just smashed the thing really hard. If it's just, yes. Okay.
Yeah, like smashing it would also, you know, create like some fluctuations of density, and that would be enough to kind of launch that nucleation. You could also break it. I use these quite often when they get old, then, you know, they kind of refuse to stay liquid anymore because it gets like really dirty inside. And one more material that you'll be surprised that it's actually not in its equilibrium state. It's the diamond. And diamond was created at crazy high pressures and high temperatures when it was created in the rocks. And at normal pressure and normal temperature, it is actually at equilibrium graphite, you know, the thing that you write with on your paper. And indeed, if we waited infinitely long, it would turn into graphite spontaneously without us doing anything. But it never happens, right? When you buy a diamond, maybe you're a bit young, but say, you know, in a few years when you may buy a diamond ring to your fiancé, then you're not really kind of afraid that it will turn spontaneously into graphite. So diamond is kind of a surprising case, and a case where you can see that metastable states can be incredibly stable for a really, really, really long time. And we will come back to that. But before coming back to that, let's now switch to phase transitions, but not in physics now, in computer science. So now you go, oh wow, okay, so what are we talking about now? So let me start with a really kind of simple example of a problem in computer science where you have phase transitions and something really interesting can be said about them. And that's graph coloring. That's a problem that a few years back when my daughter was in her first grade, I came to the class and explained to them what graph coloring is about. So that, you know, that I can explain to a 6-year-old. So that's a great example. So I'll start with coloring a map. So this is the map of regions in Czech Republic at some point when I created it in 2000 something. And the rule here is that you have these different regions, and when they are neighbors, you don't want them to have the same color because otherwise you would not see the boundary between them anymore, right? The border, you want to see kind of the border. And so I give you 4 colors in this case. You know, I could give you the map not colored and ask, you know, can you color it? Okay, this is something that 6-year-old can try, right? It's not so easy. For this map, it took me probably like half an hour to kind of arrange things properly to find things that are consistent. And that's how it looks like. Now, what is interesting about coloring of maps, so something that is on a plane, planar maps, is, you know, this is one of the famous problems in combinatorics, that actually since 150 years or 170 years or so, we had a conjecture that 4 colors are always enough to color a map. Of course, if you have more colors, it's easier to color it so that neighbors do not have the same color. For 5 colors, that's like an exercise. If you go to math phys in a first or second year of discrete math, you will prove that you can color with 5 colors, a planar map. But if you have 4 colors, till like 50 years ago, we didn't have a proof. And the proof that we got from Appel and Haken is one of these famous examples of computer-assisted proofs. These days we have a simpler one, but back then it was computer assisted. It's a really, really tough problem to prove something about. But I will not be talking about maps. I will be talking about graphs. So how do I create a graph from a map? That's simple. I just keep the color but make it just a point. For every region I make it just a point. And then I put edges, these like black edges, between the points that were actually belonging to two regions that were neighbors. So if they have even just a piece of border together, I put an edge. And then the rule of the game is that if there is an edge, the points on the two ends of the edge should not have the same color. Okay, that's graph coloring. This is a graph. If I now forget the map, this is a colored graph. And this is another colored graph, a different one. On the right and on the left, it is actually the same graph. Because when I talk about graphs, I don't really particularly care about where I put the different points. The only thing that is important is who is connected to who. And this table of who is connected to who, that's the description of the graph. That's the only thing I care about. I don't care about whether I place them in a circle or kind of randomly scatter them on a plane, or whether I don't draw them at all. I just store this table of who is connected to who in a computer. And now if we take generic graphs, so now the edges can be crossing. The particularity of the maps is that they can be drawn with the edges not crossing. But in general, if we put many edges, they will have to be crossing. It's not possible to draw them without crossing. And so such generic graphs where edges are crossing at will, actually finding whether you can color them with a given number of colors is one of these famous NP-complete problems that in computer science are kind of the, beasts of hardness that we really don't know, and we think that there are no algorithms that would basically be much more efficient than just like trying all the options. You take the first point, you try the 5 colors. You take the second point, you try again all the 5 colors for all the previous 5 colors. And so on and so on. But you see that this is exploding. The number of options you need to try is exponentially exploding. So as soon as your graph will have, I don't know, 50 nodes, you will need the biggest computer in the world, and in 100 nodes or 200, you will not be able to do it anymore. So that's, in principle, it's an algorithm to solve this problem, but it's a completely useless one. So the question is, can one actually do it faster? And we think we cannot in general. In general, that is, if somebody comes with some kind of a worst case graph, some adversary chooses for you a graph that is really hard. But the question that we studied, and that is back connected to physics, is actually what happens if the graph is random. So what is a random graph? That's very simple. You have the nodes without edges at first, right? And then you put the edges. And for every possible pair of nodes, you have some probability p, and you decide with that probability whether or not you put the edge. The probability is the same for every edge, and you go like that through all the pairs, and for each of them you draw, you have a dice, and you roll your dice and decide whether the edge is put or not. And then once you went through all the possible pairs, you end up with a graph where some edges are there because the dice rolled one way, and some edges are not there because the dice rolled the other way, and that's your random graph. So when you have a random graph, you have 2 parameters. You have the number of nodes, and then you will have the number of neighbors that every node has on average. Right? And we will call this number of neighbors, that is this number C here, the degree C. The average degree C will be the average number of neighbors that I got when I drew this graph. And now the question is, how hard, algorithmically, is to color such a random graph? And that's a question that was posed, 30 years ago, not so long as, I don't know, say some physics things have been done. And what is happening for this coloring of random graphs, so that I try to sketch here, is as a function, so on the x-axis here you have this average degree C. So how many neighbors every node got on average. And on the y-axis here, the full lines, is actually the probability that such a graph is colorable with 3 colors, say, with a given number of colors. And you see that when you have very few edges, there are very little constraints about who cannot be the same. it's almost always colorable. The probability is 1. When you have very many edges, there are so many constraints that with a limited number of colors, you cannot color the graph. And in between, depending on the size of the graph, that's the numbers up there, 100, 70, 50, the different colors are different sizes of the graph. You see that the bigger the graph, the sharper is the drop of the probability from 1 to 0. And if you actually went to bigger and bigger graphs, this would be a jump. And this would be a first-order phase transition. Just like in water, when water, say, freezes, the density discontinuously changes. Or when water evaporates, the density discontinuously changes. And the probability here plays the role of this density and discontinuously changes from 1 to 0. Now you could say, okay, it just discontinuously changes. It's not enough just something discontinuously changes to have a phase transition. In physics, phase transitions are closely linked to how fast or slow actually is the dynamics around them. This is something called critical slowing down. That's something that we teach at university, when we talk about phase transitions. And here you have, interestingly, something very similar. There's the dashed lines here. What the dashed lines are, that's actually you take some heuristic algorithm, some algorithm that somebody thought is a good algorithm to solve this problem, and you plot the time, how long this algorithm needs to run. And again, the different curves are the different sizes of the graph. And you see that the time is very big around that phase transition. It takes really long time to decide whether the graph is colorable or not around the phase transition. And that is exactly the analog of this critical slowing down. Here, instead of the dynamics being, the physical dynamics being slow, it translates into you need really long time to solve this computer science problem. And here, this is something that in the 90s have been described where actually this behavior comes from in these papers in Nature and Science, which are the two major venues where we in science publish really, really important results. And in particular, this second one on the right, in 2002, that's a paper where, when I read it, when I was a master's student at MatFis at that time, I was mesmerized. I want to study this thing. This is just amazingly beautiful. And what they found in those papers is that on a very fundamental mathematical level, this graph coloring problem behaves as a glass. The nature of the phase transitions there are really similar as what you need to do in physics to describe the glass in the window, how that is behaving. And that was fascinating. And okay, I read that paper, I contacted the first author of it, did my PhD with him, and this is kind of the picture from my PhD thesis about graph coloring. We actually uncovered a whole series of phase transitions. I will not be explaining this one in detail, but there are actually, besides this like colorability or satisfiability phase transitions that I mentioned on the previous picture, there are at least 3 and several other ones that are really important for different properties of this problem. Okay, I could talk for hours more about this one, but I will switch to a slide, to a second example. Okay, we will go away now from graph coloring. I will switch to a second example because I want to get to the machine learning. And this one is kind of getting us a bit on the way, because this problem that I will introduce to you as a kind of a card game, it will be a game between you and me. It's an actual problem in machine learning, a very basic one that I teach in my master lecture on machine learning for physicists. So what is this card game about? So imagine we have people in the room, like you, okay, 15 in my slide, say 30 in the room, and I have a deck of cards that have either +1 on them or -1, roughly the same number of each, okay? And I go around and I give each of you one card at random. I don't see the cards, you do. You see each other's cards and your cards. The game will be I have to guess your cards. Okay? I gave you the cards, I was not cheating, I didn't look at them, and now you have your cards, and I will be guessing which card you have. But I'm a physicist, not a mathematician, not a magician, right? So I need some information that I can use to compute something about what were your cards. So I need something more. So what will be the information that I get from you? I will not be asking you what are your cards, but I will be asking you the following. I will pick some pairs among you, pretty much at random, as when I was creating this random graph. So I will go you two, and I will give you a dice, for instance, four-sided. The graphs that I have later are for four-sided dice. And I ask you, okay, do you have the same cards or not? But before you answer, roll the dice. And if you have 1, 2, or 3 on the dice, you tell the truth. And if you have 4, you lie. And you don't show me your dice, but you follow the rules. You tell the truth. It's the dice who decides. It's not you, right? So you tell me, are they the same? Yes or no. But you tell the truth or you lie, depending on what was on the dice. Okay? Fine. And I pick some pairs, some number of pairs. I have n people. I will have some constant times n questions, say 5 times n questions, or pairs, or 10 times, etc. Some number like that, we will see. And so for some pairs, here I just added some pairs, and for them, in yellow, I mark the ones where the dice was 4, so those lie. So they say -1, even though, for instance, their cards were the same, or they say +1, if their cards were different, they lie. And those that are not yellow, they take +1 if the cards were the same, yes, and -1 if the cards were different. No, they are different. Okay? And then, this is still not what I observe, because I said I don't observe yellow, white, the dice. That's you who roll. You just don't cheat, you roll. But you don't show me the dice. That would make my job very easy. You just, you forget now about the people. You just imagine the graph. And now you hide what were your cards, and you hide who is yellow and who is white, which pair drew 4 and which doesn't. So all I observe are the answers yes or no. That's all I have. And I don't have the cards, and I don't have the dice, what was rolled on the dice. And now here is the game. Now my job is to take this graph and split the class into 2 groups so that most of the people in the group, in one group, have the same card. Okay. So now a quiz. Okay. How many questions do I need to do certain, to have certain performance on this thing? So let's just, for instance, look at the first line. So there I'm asking, a bit more, I want to do a bit more than 50%, to be right in a bit more than 50%. Because of course, if I split the room at random, then I'm right in 50% because, okay, there were only 2 values of cards, so with probability 1/2, I guess right. Okay, so random guessing is 50%. So I want to do better than that. I want to do just a little epsilon better than that. How many questions do I need? Like any number of questions, like 0 plus epsilon times the number of people? Or do I need half plus epsilon? Half plus epsilon number of questions is basically everybody gets asked 1 question on average, right? And half because 2 people get asked questions. Or do I need more, like 10 times the number of people questions to be actually, intuitively one would say I don't need much, right? To say a bit, maybe I don't need much. And if I want to classify 79% of people correctly, how many questions do I want? And if I want to do 92% correctly, how many questions do I need? So it's not so intuitive, right? What's right here? You could guess, okay, fine. But I will tell you the answer in a few slides. So how do we solve this? And now this is where the physics come in, kind of surprisingly. Because you would think, oh, this is some like math problem or computer science problem or maybe statistics problem. So you would not be here in this building at MatFis, right? You would go to Karlin or Malá Strana and you would ask your colleagues there, your friend or, okay. And you would ask, in computer science, mathematics, statistics, do you know how to solve this problem? They would maybe have some ways, some algorithms, like principal component analysis, etc. That would not do so bad, but if you ask them, can you do it optimally? Can you really do something if I have many people in the class that no other method can do better? Then they would go, no, I don't know, this is difficult. And in physics, this is a problem that we wrote a paper about it about 10 years ago, and how actually did we come up with the solution? goes back to the physics of glasses that I was mentioning, and to the work of Giorgio Parisi in Rome, who actually solved this problem, or a problem that ends up equivalent to this problem 40 years ago, and got the Nobel Prize for it last year, in October. And the statement of the Nobel Prize says that, Parisi's discoveries in random complex material and phenomena, these random complex materials are these glasses and spin glasses, it's not spelled, but that's what they mean, not only have applications in physics, but also in other very different areas, such as mathematics, biology, neuroscience, and machine learning. And the problem that we are talking about here is a problem of machine learning. It's a more general class of problems that are called clustering. When you have data and you want to kind of split the data into classes. Here we had the class of the +1 card and the class of the -1 card. But this is a much more generic problem. And when we actually go, I said that this is really, this problem, this very card game that I defined, is equivalent to a paper of Parisi from the 80s. And what we kind of did 10 years ago, we just realized that and went to that paper, redone the calculation, changed a bit here and there because it was not like exactly the same definitions, etc. And then had the solution. So again, this is something that we teach at the master degree. I will not be teaching you how we do that like today, but we know how to do that, and I can draw a graph that corresponds to the solution, where on the x-axis, I have the number of questions per person. So that was in the quiz, right? How many questions do we need to do certain performance? And on the y-axis, there's the percentage of correctly guessed cards. And you see it starts at half, because half is the random guessing, half is trivial. And it goes up to 1. 1 means that I get everybody right. Well, I cannot get everybody right, because since I was kind of choosing the edges, the pairs at random, maybe I completely missed him, right? Just by random, I didn't ask him any question, and then I have no information about his card, and okay, I will never be able to do better for somebody for whom I didn't ask any question better than random. But for the others, I asked many questions, and this gives me the performance. And now you see this shape of the curve. It actually sticks to half, up to number of questions per person 2, and then goes up. It doesn't go smoothly up from 0. It actually needs to reach 2 questions per person. And think here that n is large. N is the number of molecules in physics. That's kind of what this parameter becomes if you think of the physical system that would represent this. So n is not 30, n is 10 to the 23. So n is very large, and you see here you have a phase transition. Again, this change from 0 performance to better, or half, random guessing performance to better than that performance, is a phase transition, a same one as you have in magnets. You know that when you heat a magnet to about 1000 Kelvin, there's the Curie temperature, right? The physicist Curie, the husband of Marie Curie. That's his work before he actually knew Marie Curie. He theoretically described this phase transition in normal magnets. And so at low temperatures, on the right here, we have ferromagnets. Magnets are magnets. And if we heat up, that would correspond to few questions in our problem, then we only have paramagnets. The magnets are not, compass will not work if you heat it to 1000 Kelvin. It will, okay, maybe compass will. You need a compass that will not melt, but we have materials like that, so if you have something that does not melt, then it won't work. It won't be magnetic anymore. So that's kind of interesting, right? That there is this, and we call this in physics the second order phase transition, because the performance does not jump discontinuously. It changes, but continuously, right? It's 0, and then it goes continuously from 0. So indeed, the magnetization in the magnets is the same. But in the water, it was different, right? The density really jumps at the phase transition discontinuously. So that is something that we call the first order phase transitions by the classification of R and S forever. Those are just names. And, okay, before going to first order phase transitions, now you see that this graph gives you the solution to the quiz. right? You just need to see, oh, it's with 2 questions per person that I start to do better than random, and at 3 questions per person that I do about this 79%, and those are the lines in the figure. The 92%, I need 5 questions per person. And so in green, right, oh yeah, I go back, sorry. I don't want to go back. In green are the right answers to the quiz. Okay, just directly read off that graph. But now, you know, what happens with algorithms and all that? And by the way, for the graph before, we also have an algorithm that actually achieves it efficiently. That's important. That's kind of what it comes with the solution. It's already included in those papers of Parisi 40 years ago, even though it's not said this way. There is no algorithm written anywhere. There is just a computation. And when you think about it with kind of our current understanding of these matters, it just directly translates. It's in essence a pseudocode of an algorithm. But in the paper 40 years ago, it's not written that way. What if, you know, first of all, can we have a first order phase transition, like the one in water, where the density jumps discontinuously in a problem, in our card game? Who knows, right? So yes, we can. And what do you need to do to make it so? You just change slightly the rules of the game. So what you need to do, for instance, so there are many ways to do it, but one nice way to do it is you actually add many zeros to the deck of cards. In the plot that will be coming, I think I have 92% of zeros in the deck of cards. So most of you get a card with 0. And I still don't see that. And then when you will be rolling the dice, if one of you have a 0, then you don't give me any information about your cards. You just roll the dice, and at random you give me +1 or -1, independently of what the other card was. If one of you or both of you have zeros, that's what you do. Right? Those pairs don't give me any information. They just give me random number. So I'm losing a lot on those. Okay, but there are still those where both of them have non-zero, and from those I'm still getting information. But remember, I don't know who they are. So I collect still this table of +1s, -1s from everybody, and I don't know who are the non-zero ones. But my job is still the same. You know? Can I somehow from that table extract who had which card? And doing that is sufficient to actually, with the same method, bring up behavior that is exactly a first order phase transition, and the curve that corresponds to the accuracy or the performance, again on the y-axis, as a function, you know, this time I kind of call it a noise, like how much kind of noise I had in the system. So I get a curve like that of, you know, some fixed points of the corresponding equations that, okay, may be a bit difficult if you didn't think of phase transitions yet, kind of on the university level, but is the same curve that we actually compute or draw when, say, at second or third year of math-phys, we are describing to students where the first order phase transition in water comes from and how to compute things about it. And we do that in the statistical physics class in like third or fourth year at university. But here, you know, what I will do though, I will just color a bit this graph into 3 different regions that actually translate this curve into what the algorithms are able to do. And the green region will be accuracy that the algorithms we have can reach. The purple one will be accuracy that no matter which algorithm and no matter how long we run it, even exponentially long, this performance we cannot reach. The information is lost, it's not there anymore, there is too much noise. And this middle region in blue, hard, where if we were running exponentially long algorithms, we do well, but with efficient algorithms, we don't know how to do it. And this is kind of a standing conjecture in computer science that actually no polynomial algorithm can do well in this blue region. And that's a big mystery. That's, you know, many people are thinking about how to say something more precise about it. It's very difficult. But the prediction that it comes, that is this way, and what exactly is the boundary of that region, that is coming basically translating these physics papers about glasses and magnetic glasses called spin glasses from 40, 30 years ago. And here, just to kind of wrap your head about what I'm talking to you about, here the algorithm wants good accuracy, and it's stuck at metastable state of bad accuracy. In the diamond, it was a bit the other way around. You were happy with the diamond, that was the metastable state, and you were glad it doesn't turn into the graphite, the stable state, because that would not be so expensive and so interesting. So the incentives are switched, but the physics or the mathematics here is the same. Why the algorithm doesn't find the good accuracy the good accuracy state, even though that would be the analog of the equilibrium here, of the state where actually the material wants to be, it's because it's stuck in this metastable state. Just like the heater was a liquid before we pinched it. Can we pinch it and make it work? So I don't have slides on that, but that's actually a line of work that we did. And you can make it work in some systems, like systems that actually image your body in the hospital. You can make them faster by inducing this nucleation in the algorithms. So that's pretty interesting. You can kind of use that intuition to improve the algorithms in some pretty interesting settings. And here yet another kind of picture to connect this hard, impossible, easy to the liquid, supercooled liquid and ice. So in this analogy, the ice is the easy and the liquid is impossible. And then when you have a supercooled liquid, you are stuck in the liquid, but you would like to be ice. And this is computationally hard. You're stuck there forever unless you induce the nucleation. But for that, you would need to change something about how you were choosing the graph. And that you can do in some relevant problems in computer science, but not all of them. And this kind of brings me to the machine learning. I realized that where's the clock here? Here, okay. So, okay, I will try to go fast through that part. So, now this clustering is part of what we call today machine learning. What is machine learning? Or some say artificial intelligence, although artificial intelligence can mean many other things. You imagine some like nefast robots or something. But anyway, the kind of technology that is called machine learning or artificial intelligence, some say is the fourth industrial revolution. It's enabling things that seem sci-fi just maybe 20 years ago. So some of the examples, when I was roughly your age, there was the Deep Blue computer that beat Kasparov in chess. And that was a big thing. That was the first time in history that a computer beat a master in chess. And it was done in a basically not such an intelligent way. It was just a big computer that explored all the moves and memorized a lot of the moves and was just doing it really fast. As you would imagine, right? Computers just do calculations faster, and that's basically what Deep Blue was doing. And back then, I was kind of starting to get curious about how algorithms work. People said, if you play Go, we are basically 50, 100 years away of beating people at Go, because Go has many more moves, and memorizing all of them just explodes so much faster that we will not have computers big enough and fast enough to be able to do that in a century. And yet, in 2015, a company called DeepMind made a computer program that beat the Korean master in Go. And that was a big thing. Another manifestation of that is Google Translate. When I came to France for my PhD, I was mentioning that paper that brought me there. I didn't speak any French. And even my crappy French was much better than whatever Google Translate was able to give me back then, from English, not speaking from Czech. Today, Google Translate is better than me in French, and now I speak pretty good French. But in written French, Google Translate is actually better than me in French. It's pretty impressive. And AlphaFold, that's something, about proteins that are kind of the constituents super important in like all living organisms. And if we want to learn actually how our bodies work, we have to understand in detail how proteins work. And there is a mystery about the way how they fold, and it's a really hard problem to actually computationally learn how they fold. And DeepMind last year released this program called AlphaFold that folds the proteins by doing machine learning. It's pretty amazing. It's opening a whole new, range of questions that people can now ask in biology. So it's doing amazing things. From a point of view of I'm still at core a theoretical physicist. I want to understand how things work. We don't understand. We can, write the code, and I can give you every single line of the code, and I understand every single line of the code. There's nothing mysterious in that. But globally, the way the code behaves, we don't know how to predict what the code will be doing. It's pretty crazy. We don't. Like there are some mysteries about it. Like to give you an example, this canonical example of what machine learning can do is you kind of draw at it, you throw at some kind of neural network a database of cats and dogs and say, okay, this is a cat, this is a dog. Learn to recognize cats from dogs on images that you didn't see before. So every kid can do that, right, in their first year of life. Without actually seeing thousands of images. They see, the cat of the neighbor and a cat in a book, and then say, oh, this is a cat. Okay, great. But for computers, this is actually hard. If you have an image, what does it mean for a computer to learn to recognize an image? Because the way computer stores an image are these pixels, right? These pixels. Like every single little, placket in that image has like a 8-bit intensity of each of the 3 colors. Okay, so that's picture for a computer is this long sequence of zeros and ones, and that's X, that's the picture. Mu is the index of the picture. If I have 1,000 of them, mu runs from 1 to 1,000. And then for a computer to learn to recognize a cat from a dog means that it must come up with a function, with a mathematical function, such as sinus x or x squared. But here it needs to be something much more complicated of x, so that if you put in x that is a cat, it gives you +1. And if you put in x that is a dog, it gives you -1. A mathematical function, just like the functions you learn about in math. When you think about it this way, you're like, okay, how do I do about that? That sounds complicated. But we can do it very, very routinely today using something that is called deep neural networks. And deep neural networks, okay, they are called deep, but there's nothing really deep behind them. Is just a very basic ansatz, like a guess form of how this function looks like. So when you are doing physical experiments and you have like points in a line and you want to fit a line through the points, you're doing linear regression. In linear regression, you're in a sense using a special form of a function that is your data times a vector that I call here W. To understand this notation, you need like first year of linear algebra, but never mind, right? But what neural network is pretty straightforward generalization of that idea. You, instead of multiplying your picture once by some parameters, you then apply some simple function component-wise, but simple ones such as, sine of that or not square of that, something non-polynomial, some tangent of that, for instance, tangent is a good one. And then you repeat it. You again multiply by a vector of parameters, and that gives you a kind of a new transformation of that picture. And then you do it several times. The number of times you do it, that's the number of layers, and that's it. So, okay, with like a first semester of linear algebra, like I assure you anybody can understand the details of how this works. And then these parameters W, you need to find good values for them. And the way you do it, you write some like distance between what you want the output of your function be and what it currently is. And then you take that distance and by descending in the direction of the gradient, that's the like stupidest way you could think to minimize a function. But you do just that. You just descend in the direction of the gradient, or against the direction of the gradient, and that sets the values of these parameters W. So it's really, really basic. That's it. And that does magic, and we don't really understand how it does so. So one of the puzzles that we don't understand about it is this picture. So how are we doing on the time? Who will be stopping me when you? 5 more minutes. 10, okay, 5 will be enough. So this picture shows you about the concept of overfitting, right? Think back about your favorite physics experiment. You have points, you want to put a line through them. But maybe they're not exactly a line, maybe they are curved a little bit. So maybe if you fit a parabola, it would kind of be better, right? And then you go, okay, why simply parabola? Maybe I could take a polynomial of higher degree, degree 3, degree 4, have more parameters. And here in this picture, I do a bit something similar. I have this curve in in red, that the points are the data that I observe, and I want to fit a line through them, the blue one. And now I'm not taking polynomials here, I'm just taking functions that are linear functions, but with one bend, okay? And if I allow 2 bends, like this in the first picture, I allow 2 of them, there's the n above the picture, I cannot do really well, 2 is not enough. But if I allow 5, 5 times the curve to bend, then I fit pretty well, right? It's kind of close to the red curve. And if I allow 10 bends, and in this case I have 10 points, then okay, I can go through every point, but then you see out of the points I'm doing really bad. So that is a very basic concept that we teach really in the first, second class of data science to students. It's called overfitting. You should not have too many parameters, otherwise there is some sweet spot in between. You don't want to have too little parameters, not too many. Somewhere in between is the sweet spot of the degree of the polynomial or the number of parameters that you kind of use. It's called the bias variance trade-off in data science. It's a very universal phenomenon. And the interesting thing about neural networks is they completely defy it. So if I actually show you the full picture in neural networks, there's the 4th panel over there. If now I take 500 bends, 500 times I can change the slope of this curve. That's way more than the 5 that seemed optimal. It does even better. And this behavior that actually the bias variance trade-off, when we have way more parameter, we actually get good behavior again. That's pretty much happening in the neural networks that solve Google Translate, AlphaFold, AlphaGo. And we don't really have a theory that would really describe why is that so. So that's a little bit like, we don't really understand many details about black holes and about the origin of the universe. I will put that question in that bag of questions. It's a really fundamental question of something that is there in the world, and we don't have mathematical formulas that would explain it. So it's called the double descent. It was described and in some really simple settings, like the spherical chicken in the vacuum, and even worse than that, was kind of understood very recently. But in the systems that are a bit realistic, we still have no idea. And not knowing things like that translate into not knowing actually how many of the pictures we actually need to teach the computer to recognize them, right? So I was mentioning, how many pictures of cats do you think a kid needs to recognize a cat? 5? Not many. Maybe it needs the cat to move a little bit, so maybe it needs to, the pictures say translated, rotated, okay, maybe. In the data sets that machine learning researchers use in their papers to show off that they do better than the others, they use, for instance, this CIFAR 10 is the name of a data set, where you have 10 categories of images, and you have 5,000 images per category. 5,000 is a lot. Can we do with fewer? We don't know. Nobody really knows. We can try. Maybe, empirically we do, but we don't have any theory that would tell us, no, you cannot do with less than, say, 1,000, or yes, you can do this performance. Like the curves that I showed in the card game, we don't have anything like that. So that's kind of interesting, and that's what we are working on. And there's some simplified settings. So I will not really be explaining the details of this one. In physics, we always do some simplified models. that put aside the details that hopefully are irrelevant, but keep in the details that actually are responsible for the behavior. And again, fishing in some physics papers that are 30 years old, we actually get a behavior with phase transitions of the very same type that I was describing for the card game, but this time in these neural networks. In these neural networks, learning to recognize cats from dogs. And in some simple settings, we can get equations and exactly describe, get some laws, understand what's happening. And then we are making these models, examining them. Are they good enough, complete enough, like the standard model? Is there everything in the standard model we need to describe how the world works? So we have our models in this field, and we are examining what we need to put in more so that they behave more like the actual neural networks that, say, Google runs to translate from Czech to English. And yeah, it's something that I am kind of working actively since the last, 6 or so years with the ERC grant. So that's something when you get to a career of a young, promising researcher in Europe, that's a grant that you will want to get. That's a grant that is very prestigious and that kind of kickstarts your career in a pretty spectacular way. It's a lot of money. You can hire a lot of students, postdocs to work for you. So mine is called the statistical mechanics of learning, and the learning there is the machine learning. And I will stop with this for the questions.